Hello everybody, my name is Vernon Hicks. I'm a senior at the University of Maryland, but this summer I'm working with Dr. Jiamin Hou here at the University of Florida, studying large-scale structure using endpoint correlation functions and GPU-accelerated computing. So, what are correlation functions? Well, simply, they're tools used by cosmologists to quantify the clustering of galaxies and dark matter in the universe. The simplest form, the two-point correlation function, simply measures the probability, above random, of finding a certain galaxy at a certain linear distance from another galaxy. And the next step up, the three-point correlation function, shown schematically in the center of this diagram, gives the probability, again above random, of finding two galaxies at two linear distances for a primary in a certain orientation, described by the angle theta. So these tools have tremendous scientific value and they can tell us a lot. For instance, one of the things that we would expect most logically to cause clustering of galaxies is gravity, which, as we all know, is primarily controlled by dark matter. So by getting a metric of how galaxies are clustering, we can get a good idea of the abundance and distribution of dark matter in the universe, which is very interesting. We can also get information about dark energy and even some particle physics topics. There is, of course, a drawback, and that drawback is computation time. So shown on this plot here is the calculation time for a three-point correlation function plotted against the number of galaxies. Both of these axes are logarithmically scaled. So we see two methods here, a simple naive loop-based method and a slightly more advanced array-based method. There is, of course, a problem here in that both of these methods, while the array method may be faster, scale with the cube of the number of galaxies. That's a problem because if we extend out to around 10 to the 6, here's a reasonable galaxy sample, we can see that the loop-based method would take about a mega-year to complete, which intense literature review has revealed to me is slightly longer than the length of this research project. So, how do we get around this? The hope of my project is the answer lies in GPU computing. So GPUs differ from CPUs, and that CPUs, the sort of standard processors in your machines, are designed to do a couple relatively simple tasks at the same time, and then move to the next step. GPUs, on the other hand, are designed to do hundreds of thousands or even millions of computations all simultaneously. And so the hope is that we can use this higher computation throughput to speed up the execution time of our correlation functions. So in that vein, I'm using Coupon, a Python package, and NVIDIA's CUDA software. So the first step is to simply implement Coupon, which is a drop-in replacement for NumPy and SciPy designed to work better on the GPU. And we can see some pretty big improvements. There is a little bit of code overhead at a very low number of galaxies. That's just basic operations that it needs for the GPU. But by the time that we get to the reasonable number of galaxies, we're seeing a lot of speed improvements over the other methods. Additionally, what's even more important is we're seeing a flatter scaling with n, which is important for extrapolating up where we want to go. The problem, of course, as you can see right here, around 10 to the 4, is we asymptote back to that n-cube scale. That's because CuPy can't actually reasonably parallelize certain parts of the code. And so that's a problem, because if we go all the way out again to our goal, we're still talking hundreds of years to complete. Still too long. So where do we go from there? The answer is CUDA kernels. So a CUDA kernel just describes a bit of CUDA code, which is essentially C++ reskinned, designed to run better on the GPU. And so the idea is you can take the complex, mathematically intensive parts of the calculation, write them in CUDA, compile them, and call them as functions in the rest of the program. That's got a lot of obvious benefits because C++ is a compiled software, which means you have a lot of speed benefits. Additionally, CUDA allows you direct control over how your code is parallelized, meaning how it's distributed onto the GPU. That's very nice. Additionally, it allows us a lot more freedom to control how memory is allocated, which is a big deal, as we'll get to in a minute, is a major bottleneck. So, implementing these CUDA kernels, we can see on the graph here, and we've got a further, almost factor of 100 improvement over CuPy, which makes it a good amount faster, of course. Scaling up, we're still looking about a year and a half for completion, which is too much. Okay, so let's parallelize more. What's stopping us? Well, I mentioned that there was a memory bottleneck. So what did I mean by that? Well, so if we look at this set of diagrams, the diagram on the left describes how a CPU might approach this problem. It starts the code, it looks at a first set of secondaries, it does all the math it needs, it stores its results, and moves on. And it keeps looping over that until it's done. A GPU, on the other hand, starts its code, it takes all the sets of secondaries it wants to calculate, runs them through on different parts of the GPU, then conglomerates its results. That's obviously a lot faster because you're doing a bunch of things at the same time, but there is a drawback. And that drawback is that you need to have all of the variables or data that you're going to use for all of your calculations stored and ready on disk as soon as it starts. That may not seem like a big deal, but that can get to a big amount of storage that you need for just variables and stuff. But the A100 GPUs on Hypergator, I hear you say, have 80 gigabytes of RAM. Surely this isn't a problem. So let's do a little bit of a thought experiment. Imagine you had a sample of 5,000 secondary galaxies, and you just wanted to store a single variable that we need for the calculation that tells you all of the possible combinations that you can make, that you have to calculate. So for the 3PCF, that corresponds to about 12.5 million unique triangles, which is a data size on disk of about 48 megabytes. Put that in perspective, it's about the data size of Led Zeppelin 4's studio album, an hour and a half of audio. That seems fine though. 48 megabytes, we've got 80 gigabytes, we're fine. All right, let's move to the 4-point correlation function. Well, that's 21 billion tetrahedrons. That's a data size of about 78 gigabytes. To put that in perspective, it's the size on disk needed to store all 11.5 hours of the Lord of the Rings Extended Edition in stunning 1080p resolution 5.5 times. That's a lot of space. And of course, that's only 5,000 partners, and it's only one variable that just tells you what math you need to do. It doesn't even do the math. If we extend to 1 million secondaries, our goal, that's a data size, even for the 3PCF, of 1.8 terabytes, which is a lot more storage than most of your laptops have overall. That's a problem. So how do we solve it? So obviously we need to then limit memory consumption. So this is a big issue because, as I said, it scales with the square of the number of galaxies. So there are a couple of technical methods that we can use, like reducing the amount at which we cache results. That means that we don't store as many of our intermediate results, keep them off disk, lower our memory consumption. We can also store indices instead of variables because we can use the much smaller data formats for them. But overall, this is sort of lower scale improvements. The biggest thing that we can do is actually a method used outside of just my work in correlation functions in general, called close partner counting. What that essentially means is that our simulation box is very, very large, of order of 1 to 2 gigaparsecs, and contains 1 million galaxies. But the cosmological principle tells us that out above a scales of about 200 megaparsecs per h, we expect the universe to be mostly homogeneous. That means that we can only focus our efforts on galaxies within about 1/10 of the box length of our primary. That cuts down a whole lot on the amount of galaxies we actually have to calculate and makes our program a lot faster to run, because instead of an 1 million cubed problem, we have an 1 million by 5,000 squared problem. We can see a schematic of what this looks like on this side of the slide here, but we're only counting partners inside of that circle. So that method obviously actually benefits the CPU method as well, because you're just reducing the amount of math you have to do. And so for the CPU method, the basic method, with all of these improvements, we see that for a realistic sample of 1 million galaxies, execution time is about 12 years. It means you start your code running, you go get a pair of PhDs, you come back and see if it's done. Implementing my improved code using CUDA and all the GPU improvements, I've gotten that down to about 25 minutes. So about 1/3 of your average lecture at the university. That's an improvement factor of almost 250,000. And it's really exciting because it means that we have code that executes in a reasonable human time frame, less than half an hour, and that means we can start using it to actually do some really interesting science. So just to recap a little bit, we now have, using CUDA and GPU computing in general, an efficient, reasonable time method of calculating the 3-point correlation function. That's exciting because it allows us to do some interesting scientific things, like, for instance, looking at simulations to study, for instance, one thing I'm interested in is halo assembly, and get some interesting data out of that. Additionally, this same software pipeline will allow us to analyze actual observed results, such as those coming out of DESI and stuff from BOSS and other surveys. That's super exciting. Additionally, I'm hard at work currently, working on developing a 4-point correlation function method using the same techniques, hopefully with reasonable timeframes. There's a little bit of extra challenge in that the 4-point correlation function scales by an additional factor of n, both in compute time and memory storage. So even more GPU computing acceleration tricks are needed to get it down running at a reasonable time. But my hope is that very soon we'll have a partner method for the 3PCF that'll also allow us to do the 4PCF, and overall see some really interesting scientific results. Thank you, everybody.